Well, standardized residuals, that's our next tool for the diagnostic steps of the regression model. Actually, we talked about residuals, how we can use the residuals to reflect like the pattern of the, by looking at the pattern of the residuals, it will reveal if there is any problem with the fitting. But why here we'll talk about the standardized residuals. Well, a complication when we use the residuals directly to see problems is that when that the residuals, they do not have the same variance across the board. So for different data points, their variance are not the same. So we would have to standardize them so that they have the same variance. It's easier for us to compare, to look. Here it has it shows the ith least squares residual. It has the variance being sigma squared times 1 minus the, what is this HII? This is the leverage of each data point for the ith data point. So that means the residual of a high leverage point will have a smaller variance than others. So if this is high, then the whole thing, the whole variance of this residual will be low. So that means the residual, the variance of the residual by itself will depending on if it's a leverage point or not. So it's not constant. That's the problem with looking at the residuals by itself. So now we look at the standardized residuals. How do we do the standardization? We just divide each residual by estimate of its standard deviation. Well, the standard deviation we already showed here, taking the square root of it. Well, standard deviation is from the sample, where we know this sigma is unknown. We estimate this S from the data. That's our sample standard deviation. Sample standard deviation. That's our S, and this Ri is the standardized residual. So that's just the residual divided by its standard deviation. Well, when you have points of high leverage, plotting the residuals will have a non-constant variance. Well, we'll look at the variance of the residuals already. It will be influenced by the leverage value, even if the errors have constant variance. So that's the problem. The residual by itself will not tell you the whole story. Plotting the standardized residual will fix the problem. Also, the standardized residual tell you how many standard deviations any point is from the fitted regression model. So if, for example, if a point has a standard residual point 4.3, then you know that this point is estimated to be 4.3 standard deviations from the fitted line. We are assuming that the errors are normally distributed so that the value is highly unusual. And we call that an outlier. Normally, like the boundary for outlier is from -2 to 2. So I said here in the small to medium data sets, the outlier is any point that has a standardized residual outside the interval of -2 to 2. So for a large data set, we have changed this to outside -4 to 4. So this is related to the critical value for a standard normal distribution. But when we have a large data set, we adjust it to -4 and 4. So yeah, this is how you use the standardized residual to determine like how far is the point from the fitted regression model. And this is also how we determine if the data is an outlier or not. Let's look at another example. I took this example from the from our textbook, Schiller's book. Well, this is a special example where it shows you where you can. Well, let's talk about the example first. You will see what is the difference from like other examples we showed. So we'll illustrate how a small number of outlying points can influence a model. Use this old treasury bonds data where we have 35 data points. So yeah, when we run a simple linear regression, I looked at the confidence interval of the slope being this, and a p-value for the model it's small. It looks good, right? That means, well, the slope, I mean the x value, which is coupon rate, is highly significant. But when we look at the plot here, we can see there are 3 data points that does not really follow your regression line, and this which means this line did not really describe your data really well. Well, it has some problem, right? These 3 data points. So let me show you the whole picture here, where it plotted the standardized residual here and labeled the data points, which data points is here. So this case is 4, 5, and 13 and 35. Well, this is 34. Sorry, it's a typo here. They have leverage value greater than 0.11. So that is to compare 4 over n. 4 over n is by the rule of thumb to determine if it's a high leverage or not. So these are classified as leverage points. And if high leverage points is also outlier, that means it's bad leverage points. And points are classified as outliers if their standard residuals are outside this interval, -2 to 2. So for our leverage point, 4, 13, and 35, they're both leverage points and outliers, so they are bad leverage points. Right, this is how we use this standardized residual to determine if it's an outlier. If it's an outlier and a high leverage, it's a bad leverage point. Sorry about the typo here. I'll correct this error when I post the slides. Well, continue this example. When we look further into this data point, 4, 13, and 35, in this dataset, it's discovered that these are flower bonds which have different tax advantage than the other bonds type. So we can expect the relationship to be different. When a new regression is done on the data without these 3 points, it looks much better. And the slope estimate now is 4.83, which is not even in the confidence interval we calculated previously when we have that 3 data points over there. So there are definitely problems with the previous model we fit. And by looking closely to the data, we find, okay, these bad leverage points, they are not from the same category, from like the bulk a part of our X, right? They are far away from those, and they are actually not of the same type. So remember our strategies. When we have bad leverage points, we either get rid of it or we fit a new model. But in this case, when we think about it, the data we have, they are not of the same category, which means we should fit different model for different category. So in this case, we remove that three bad leverage points and refit the data. So that's the strategy we take for this special case. And now in the new fitted data, we can see that the standard residuals, well, sorry, I meant to say now it reflects our true relationship between the bid price and coupon rate for the same, for the data which have the same tax status, which from the same category. Well, if we look at the standardized residual again, we can see that well, we have some non-constant error here because we see one data points jumped out of the range of -2 to 2, which are our next step for the regression diagnostics. But before that, I have some comments here. Well, points should not be blindly removed from the model just because they do not fit. In this example that we saw, I explained that why we removed it and refit the model, but it's not in all the cases you should just remove the data blindly. That's not right. Sometimes the outlier and bad leverage point, they're giving you information, flagging some potential problems. So in our case here, we see there are different categories. We should fit different model for them. And outliers can often point out important things such as alternative models in which those points are not outliers, which is exactly what we have seen in this example. Well, another concept for assessing the influence of a leverage point is called Cook's distance. Well, before I talk about the definition of the Cook's distance, we pay attention that this bracket with this I, this subscript means that the I's case has been deleted from the fit model. So this yj hat with this subscript I in the bracket means the j's fitted value based on the model fit with the i's case deleted from the data. So we fit the data without this i's data point. Cook, this person, proposed a measure of the influence of individual data points for simple linear regression. This is defined by its sum over this yji hat minus yj hat. Well, this yj hat is just normally when we fit the model and get the predicted value for j's data point. And this yj with this subscript bracket I is when we remove the i's data points and fit the data to predict this yj hat. Well, it's a summation of their squared difference and divided by 2 times the standard error sample variance, because this s squared. And it can be written as this ri squared times ri squared divided by 2 times this hii divided by 1 minus hii. So it has some relationship with the leverage and the residual, standardized residual. So a large value of di can be caused by either a large value of the standardized residual, where this ri square, or it can be caused by a large leverage value. Like if this hi is big, this di will also be big, or by both. Big standardized residual and big leverage. average value. Well, this is how, well, we also have a general guideline. How are we going to use this Cook's distance, DI? It's generally recommended to use this 4/n-2 as a cutoff for noteworthy value of DI. Well, in this plot on the right, it showed you a cutoff of 4/35-2 in our example, which is 0.121. And we notice this 13 and 35 and 4, these data points are noteworthy. But if, so I have some notes here. If the largest value of DI is substantially less than 1, deletion of a case will not change the estimates by much. So this is how this DI is, how is this DI used to assess the influence of the data point. So if DI is small, is substantially less than 1, remove it will not cause much change for our estimate. Well, in practice, it's also actually important to look at the gaps in the values too. So for example, most of them are just like closely, like really, really low, like small, close to 0. But there is one really high, then that's definitely noteworthy point. But like here, use this cutoff is just a general rule to determine if some point is skeptical. You should take a further look at them.